All right, so today's lecture is going to be on consonance and dissonance theory. So I'm sure that most of you are familiar with what consonance and dissonance are. Basically, consonance is when you are playing multiple notes together and they sound good together. Dissonance is when there's tension when you play multiple notes. Sounds bad. These terms are kind of thrown around a lot in music school, but nobody really talks about what they are, how to quantify them, those sorts of things. So that's what I want to do today. I want to provide a little bit of math and a little bit of a conceptual understanding for what exactly consonance and dissonance are. Caterpus, are you okay? Are you in the stream? Just kind of click on my name and like view. Okay, cool. All right, so there are a couple theories for what consonants are, and the earliest theory for consonants, at least Western consonants, because consonants does vary by culture. Some cultures consider different intervals to be consonant or dissonant. So today we're just going to be focusing on Western consonants mostly, and consonants doesn't vary that much by culture, so the ideas here should be generalizable pretty easily. So Pythagoras, as you guys might know, based his tuning around the interval of a fifth. So a fifth has a ratio of 3 to 2. So what that means is, let's say I'm playing a C, and let's just say that my C is 200 hertz. I know that that's not what a C is, but it's just going to be easier if I use an easy number. And then if I played the G above it, that means that the G would be 300 hertz. I think that this is a pretty common idea. I don't know how many of you are familiar with thinking about intervals as ratios, but that's kind of what the ratio means, is basically I can multiply the bottom note by 3 over 2 and I'll get the higher note. So Pythagoras wanted to construct all notes using the ratio of 3 to 2. This is also called three-limit tuning. So I'll title this three-limit tuning. Now later on I want to go into a more in-depth lecture on different systems of tuning and why we might choose to use or not to use Pythagorean tuning. But for now, just know that this is how you construct it. So we would start with C, and then we would build G by going up by that ratio. We would build D by going up that ratio, A, and then we would just keep going along, the circle of fifths until we constructed all the notes. Now, unfortunately, this does cause a couple problems. So Pythagoras theorized that notes that have small intervals, or not small intervals, but nice intervals, nice ratios, sound better. So, for example, C to the C above it in Pythagorean tuning has a ratio of 2 to 1, okay? 2 to 1 is a really great fraction, and octaves do sound really great, so that makes sense. As we already said, if we have C to the G above it, that ratio would be 3 to 2. Again, very great ratio. That's true. A perfect fifth sounds very consonant. Now let's say that we had C to D. This would have a ratio under Pythagorean tuning of 9 to 8. A little bit bigger numbers, and the major second has really bad consonants. It's a very dissonant interval, generally speaking. Now, where things start to become a problem is the more fifths you move away from C. In Pythagorean tuning, the interval of a major third, C to E, has the ratio 27 over 16. Now, I don't know about you, but the ratio 27 to 16 is a pretty big number. No, sorry, that's not C to E. That's C to F. My bad. A perfect fourth. Now, I don't know about you, but 27 over 16 looks like a pretty bad ratio. Shut up. The issue is the perfect fourth really isn't dissonant. Now, I know blah, blah, blah. There's some, Baroque counterpoint rules about don't use the fourths or stuff like that. But generally speaking, the perfect fourth is a pretty consonant interval. So you can see the Pythagorean tuning sort of breaks down under this simple mindset of smaller numbers equals better. Is everybody muted? Sarcasm, I think you're breathing in your mic. If you breathe into your mic again, you will be banned forever. Okay. So modern tuning, I shouldn't say modern, but tuning in early classical music is 5-limit tuning, not 3-limit tuning. So in addition to construction with the fifth, we also use construction with the major third. And the major third is defined to have the ratio 5:4. So the reason we call this 5-limit tuning is now all of our ratios can have 5s in them. Previously, it could only have 2s, 3s, and multiples of 2 and 3. And in general, you can have any limit, with the limit being some prime number. But just intonation uses 5-limit tuning. So if under 5-limit tuning, what we can actually do is a lot of really great things. So let's take, the ratio of a, let's just compare the major third for a second. So the major third under Pythagorean tuning did not have the ratio of 5:4. It had, let me get a calculator real quick because this is going to be a nasty number, but think about stacking fifths. How many fifths would we have to stack? We would need to stack C to G, 1, D, 2, A, 3, E, 4. So in the numerator, we would have 3 to the 4th power, which is 81, an absolutely horrendous number. And then the denominator, we would probably have 64, I think it is. I'm almost positive that's the ratio for a major third. So a major third comes up with this absolutely horrendous fraction in Pythagorean tuning. And so we can see the 5-limit tuning actually simplifies this up quite a bit. And similar things can be done for other intervals. I don't really want to get too much into tuning because, again, I'd like to do a full lecture on tuning later. So we have this idea of small numbers and 5-limit tuning creates good things. However, that still doesn't entirely capture it. Let's say that we had this perfect fifth, which is 3 to 2. In our modern tuning system of equal temperament, this interval of a perfect fifth is actually slightly flat. So maybe in our system, we have the ratio 299 to 200, which is slightly less than 3/2. So maybe I should put a less than symbol there. However, it's not off enough for the ear to say that's disgusting. So we have this issue, this apparent contradiction here, where we have a 299 to 200 ratio, has massive numbers, should be horrifically dissonant, but in reality, it just sounds like a 3 to 2. So there's a lot of limitations with this thinking because it doesn't really take into account rounding and all that sort of things, because the human ear just rounds to the nearest perfect interval. So this is where we start to get into the work of other people like Euler. So before Euler, consonance was not really considered mathematically too much besides the simple idea that small numbers are better. They were considered by their interval names. So theorists such as Johannes de Garlandia in like the 1300s or something wrote one of the earliest books on music theory, and he basically just listed all the possible intervals and said which ones he thought was dissonant and which ones he thought was consonant. Not very helpful to someone looking to really understand the why, but certainly useful to the composer who just needs the how. So here's where we get into the work of Leonard Euler, because Leonard Euler is one of the most famous mathematicians of all time, definitely up there in the top 5. And he did a lot of things. He was not just a mathematician, and one of the things that he liked was music on the side. As far as I'm aware, I don't think he played any instruments, at least not very well. But Euler did like math, and there's a lot of math in music, so Euler said, why don't we try to explain consonance? So what he did is he sat down and he thought, what is the most consonant interval? I should probably check chat to see if there are any questions. I realize I haven't been checking. So let's see. Oh, yes. No, 4 to 3 does work in Pythagorean tuning. My bad. That is true. Euler did not compose anything as far as I'm aware. Is math mastery a must for composing? Absolutely not. I think that math mastery can make you more informed in your composing and make you more aware of a lot of things like tuning and timbre, but you don't need to. No, I'm not saying boiler with a B. It's Euler. I'll write his name on screen for you. It's spelled like Euler, but it's pronounced Euler, like this. So the fractions represent the ratios. So again, I'll give the example. If we have, let's say we have A at 440 hertz. And then we have the E above it. In just intonation, or in Pythagorean tuning, we would have 660 hertz. This means that the perfect fifth has a ratio of 3 to 2. So some people write ratios like this. I'm just going to do fractions because I think the colon thing is kind of stupid. Just my opinion. Yeah, so basically, if, let's say we had a couple octaves down, maybe A was 220 hertz. Lower down, then E would be 330. So intervals are not just a gap of like, oh, all perfect fifths are 50 hertz apart. That's not true. Intervals are a ratio between the hertz. So I'll clear my screen. Any more questions? Let me join chat again. Why do people write it as a fraction if ratio is the correct form? Well, if you notice, you get rid of the F, C, and N, the word fraction turns into ratio. So they are the same thing. Now 3 divided by 2 and 3 colon 2 all represent the same thing. Could you do a microtonal tuner for the tuning lecture? Do you guys know of any that I can find online to pull up and play for you guys? Let's see if I can tall kite. Okay. Let's see. I'm going to have to end the stream and rejoin it so that you guys can hear my computer. Oh goodness, is this going to be a download? I don't know if I can download this right now. I think I'm going to worry about listening to things later, but yes, in future lectures, especially the tuning theory lecture, I definitely plan to do stuff like that. But you guys can try messing around and listening to these sounds on your own time if you'd like. Are there any more questions? Otherwise, I'm going to move on and start talking about Euler's theory. I'll take that. Oh, some more typing. I'm going to take that as a no for the time being. All right, so Euler lived in a time where 5-limit tuning, at least in terms of, limit tunings, was the predominant system. Of course, equal temperament. Is there a quick way to mute the VC when someone's joining or leaving? Not sure what you mean. Anyway, so at least in terms of like just intonation and that sort of thing, 5-limit was the way to go in Euler's time. So he worked with 5-limit. So Euler basically sat down, and to start his consonance theory, he asked himself, what is the most consonant interval? And I think the answer to this is somewhat too obvious. It's just the unison, the ratio 1 to 1. Obviously, any note with itself is going to have perfect consonance. So what he's going to do is he's going to define his function g. So he wants to create a function g which takes in a ratio and spits out a consonance value. He's going to say that g of 1 over 1 is equal to 1. So 1 is the most consonant sound possible, okay? Now, what's the next most consonant interval? He's going to say it's the octave. Euler believes the octave is the second most consonant interval. So he's going to assign g of 2 to 1, 2 over 1 to be 2. And we can continue on this. So if we stack octaves, let's say we have a 2-octave gap. A 2-octave gap would be 2 over 1 times 2 over 1 is equal to 4 over 1. That's a 2-octave interval. And he's going to call this 3. And we can continue on and on and on, stacking fractions and just giving them extra values, extra numbers like this. So at this point, we have to make, 2 to 1 basically means if I have A is 440 hertz, the A above it is 880 hertz. It's double the hertz. Can you remove speaking perms that everyone rolls so there's no accidents? If one of the mods wants to do that, go ahead. I'm not going to bother with it right now. Okay. So we have the start, but we don't really have anything for intervals that are not octaves. So let's say we do the perfect fifth. The perfect fifth is a great one to do. So this is again another decision point for how we're going to define the function. And Euler believes that the perfect fifth is approximately as consonant as a 2-octave ratio. So he's just going to define that Euler's function of the 3 over 2 ratio is equal to 3. Okay? So basically his thought behind this, I'm sorry, not 3 to 2. This is not for the perfect fifth. This is for 3 to 1, which is a major 12th, which can be thought of as an octave plus a fifth. So we're going to define g of 3 to 1 to be 3. And he also believes that g of 5 to 1, which is, good lord, what interval is that? A 17th, I think, is going to be equal to 5. Major 17th. There should probably be capital M's if it's going to be major. So perfect 12th, major 17th. How do you guys feel about that? So those are kind of the starting assumptions with our system. Every time we add an octave, we're going to add 1 to the consonance value. And we're going to start with the idea that the perfect 12th has consonance 3, and the major 17th has consonance 5. So let's construct some new intervals. Is there a page clear? Yes, there is. Beautiful. So, I should say one further note is in higher limit tunings, we can construct the rest of the primes just by doing this. So for any prime p, we have that g of the prime p over 1 is going to just be the prime p. Okay. So let's construct some other intervals, and maybe you'll see some of the reasoning for Euler's function, which is a little complicated to fully state. So let's start with the interval 10 to 1, okay? 10 to 1, I want to use fractions. 10 to 1 is not a prime. 10 is not a prime number. Yes, a 12th and a 15th have the same level of consonance in Euler's mind. They both have consonance 3. No, 15th was not assigned 5. 15th is a 2-octave interval, which means it's assigned 3. Whatever a 4-octave interval is assigned 5. Basically, number of octaves plus 1 is how consonant Euler thinks it is. And I guess that makes sense. I mean, the wider you play your octaves on the piano, the less like harmonious and joyous it sounds, you know? No, a higher number is less consonant. It's like golf. You want to have a lower number. That's why the unison is the only interval that has consonance 1, because it is the perfect resonant whatever nonsense. So let's do 12 to 1. So we construct the 12 to 1 ratio by multiplying together an octave and a 5 to 1 ratio, which again is, what is it, a 17th or whatever, 2 octaves plus a major third. We want these to have, we want this to have the same softness as the interval 5 to 2, because we construct this in a very similar way. We start with the major fifth, and then we divide by an octave. In other words, we go an octave down, if that makes sense. So we start with this, not major fifth, major 17th or whatever, and then we go halfway, 1 octave down, which is the same as dividing by 2 over 1. So we want these to have the same value of softness, since we construct them in a very similar way. So what we're going to do is we're going to take the least common multiple of the notes in our ratio before we plug in. So for those of you who haven't been in math class for a while, the least common multiple is basically like this. We have the least common multiple of, in this case, 5 and 2, maybe. We look for the smallest number that has both 5 and 2 as factors. In this case, it's 10, because 10 has factors of 5, and it also has a factor of 2. Let's say, I'll just do another couple examples just to get you guys familiarized. Let's say that we had the least common multiple of 6 and 4. The least common multiple would be 12, because again, 12 has 6 as a factor, and it also has 4 as a factor. 6 times 2, 4 times 3. Let me check chat to make sure everybody's okay. No, there's actually a lot of uses in number theory and abstract algebra for the least common multiple stuff, mostly number theory, but the consonance value is needlessly confusing. Why do we want that? I need to scroll back a little bit. Why do we want, I'll start with HK's question. Why do we want them, which I assume are the 2 octave interval and the major 12th, or perfect 12th, to be equally consonant? There's no real reason. It's just Euler believes that they sound equally consonant, and I think that if you listen to them both, they do sound similar. It's just a starting assumption. It's by no means perfect. Oh, 10 to 1 and 5 to 2. We want them to be consonant because we construct them with the same intervals. So for, let's say we have a 2 octave gap and a 3 octave gap. We construct the 3 octave gap by stacking 3 octaves, which is more steps than constructing a 2 octave interval, which only takes 2 octaves. So 10 to 1 and 5 to 2 are constructed using the 5 to 1 ratio and the 2 to 1 ratio. They're using the same steps, just in different directions, if that makes sense. Yeah, like total distance. Let's see, Caterpus had a question. The consonance value is needlessly confusing. I am confused. Can you clarify, Caterpus? To not use the negatives in labeling the consonants? I think it's helpful to have a starting point where one ratio is the most consonant, because the unison really is the most consonant interval. You cannot get more consonant than a unison. There's literally 0 dissonance there. Why is it going down as the number grows bigger? Golf. Yeah, the idea is that we can have a well-ordered set for our consonances. So each consonance is being given an integer value. Well, okay, if we wanted to have bigger numbers be more consonant, then we would have to assign the unison to be -1, and then all of these to be -2, -3, -4, and what's the point of that? You're just adding a negative sign for no real reason. Okay, so is everybody cool with what the least common multiple is? I know it's probably been a hot second since math, but so what we're going to do is we're going to take the least common multiple of our intervals. So the least common multiple of 10 and 1 is equal to the least common multiple of 5 and 2, because they both are 10. And so now what we're going to do is we're going to make a little bit of a compromise here. So what we're going to do is now we're going to plug in number 10 into our function, but we don't know how to deal with that yet. So what we're going to do is break this number that we get into its constituent parts, which are 5 and 2. 5 times 2, right? What we can do, well, they're both to the first power. What we're going to do is we're going to subtract each of our primes by 1. So we're going to do 5 minus 1, and we're going to multiply it by the exponent, which is just 1. We're going to do the same thing with 2. We're going to do plus 2 minus 1, and then multiply by the exponent, okay? Let's see what's happening in the chat. Why go 1, 0, -1? I'm not really sure what you mean by that. What we're doing, SIY, is trying to assign a consonance value for the interval 10 to 1 or 5 to 2, which is the same thing. So Euler's construction here does seem a little arbitrary, and to be honest with you, it sort of is. But what's important is that it does actually accurately describe a lot of things. So once I'm done explaining the process that you do, I can explain its point. So if you actually calculate this, you get 4 plus 1 is equal to 5. So the interval of 5 to 2 has a consonance value of 5. Let's do another one just for the sake of it. I think maybe it'll be helpful to do multiple. Let's do the ratio 5 to 4. So 5 and 4, and if you remember, this is a major third. So the interval for 5 to 4, we need to take the least common multiple of these guys, and as you can see, it's 20. So now we can plug in g of 20, which is going to be 20 breaks down into 5 to the first power and 2 to the second power. This is like factorization, if you remember that from your grade school math. So now what we're going to do is 1 times 5 minus 1 plus 2, because we have this exponent here, times 2 minus 1. And then if we calculate this, we ultimately get 4 plus 2 is equal to 6. So 6 is the consonance for the major third, according to Euler. Any questions on that? Yeah, no, it 100% is just arbitrary where you start from. Euler just decided to start from 1. Yeah. So this is how we calculate this. So if you, if there's any, I know there's a couple more mathematically literate people. So in total, g of a ratio, so let's say R1 to R2, g of a ratio is equal to g of the least common oh goodness, my handwriting is getting terrible, g of the least common multiple of these guys. And what this is ultimately going to be is 1 plus the sum. Oh, I forgot to do that. Sorry, guys. For both of those intervals, you need to add 1 at the end for whatever reason. Yeah, that's why you should prefer starting from 0, because Euler started at 1, you actually have to add 1 to all your intervals. So the major fourth should have a value of 7, not 6. And similarly, the 5:2 ratio should have a consonance of 6, not 5. So n equals 1 to whatever. I shouldn't do that. I'll just do sum over k. So this is big sigma. This is for mathy boys of ak times p to the k minus 1. After you break your least common multiple into like these guys, if that makes sense. So ak is the powers, and pk is the constituent primes. So pk is going to be 2, 3, 7, whatever, and ak is going to be the power of that particular prime. So if you had the number 49, then your pk would be 7, and your ak would be 2. So not necessary that you understand sigma notation and all that. This is just for the sort of the mathy people. So notice this least common multiple thinking actually does a lot more than just ratios, because we can take the least common multiple of as many numbers as we want. So why don't we try taking the consonance value for the major chord. So a major chord can be written as the following ratio, 6 to 5 to 4. In other words, if we started with A is equal to 440 hertz, then C sharp is going to have to be 550 hertz, and E would be 660 hertz. So this is the just intonation tuning for the major chord. I mean, it's common enough. I mean, that's at least what I see in my experience with number theory as far as P sub k and A sub k. I mean, P stands for prime. I don't know what A stands for. A stands for letter of the alphabet, I guess. So this is our major chord. So what if we take the least common multiple of all of these guys? 6, 5, and 4. And we can see that this would actually, does anybody want to give me a number? Okay, too late. It's 60. So the least common multiple for the major chord is going to be 60. So now I'm going to clear all this junk out of my way. We can do the Gradus function. By the way, I should have mentioned this way earlier. The G stands for Gradus. I have no idea why Euler decided to call the consonance function the Gradus function. Yeah, that's literally what it is. I have literally zero idea why Euler called it the Gradus function, but it's called Euler's Gradus function. Maybe there's some connection with the word grade and like function, I don't know. Maybe it's Gradus, I don't know. In any case, that's what it's called, if you ever needed to know that. So G of 60, let's break that down again, is equal to 5 to the 1. So 60, I should say, I shall put that down there, is 5 to the 1 times 3 to the 1 times 2 to the 2. So we have 5 minus 1 plus 3 minus 1 plus 2 times 2 minus 1, and then plus 1, because we just have to do a plus 1 at the end. Thanks, Euler, for starting at 1. And so ultimately we get 4 plus 2 plus 2 plus 1 is equal to 9. Oops, I clicked off of it. 9. So 9 is actually not that bad, all things considered. Comparing it to some of our other intervals, you remember the major third had consonants of 7. So this actually gives a decent theory for how consonant chords are in general, which is pretty cool. So just for one last example, let's look at a dissonant interval, I suppose. So maybe we can do a minor second. So there's a couple different ratios that you could use for a semitone, but right now we'll just do 16/15. So what's the least common multiple of these guys? Unfortunately, you just have to multiply them together. 16 times 15 is 240. That's pretty bad. Let's see what happens. G of 240 is equal to 5 minus 1 plus 3 minus 1 plus, we have 4 2's in this case, so 4 times 2 minus 1 plus 1 is equal to 4 plus 2 plus 4 plus 1 is equal to 11. So the minor second is more dissonant than a major triad, according to Euler. A braid of hair? Bruh. So, generally speaking, Euler's function pretty accurately describes things in nature. Again, it does not really account for that sort of thing I talked about earlier, where you're just slightly out of tune. You know, if we put in 299 over 200 into this function, we would get probably a really massive number. Yeah, 3 notes in general is going to be a lot worse than 2 notes. You'll notice that also in general, the more overtones are in your chord, like the more notes that are in the same overtone series in your chord is going to give you a smaller value for the Gradus function. Yes, psychology does play into this, which is why this isn't a perfect system. As you might know, in the 1300s and in medieval church music, sometimes even major sixths were considered to be dissonant, and major fourths, or perfect fourths, I mean, were considered to be dissonant. So, as with anything, there is some variance based on culture, but there's a lot of similarities between cultures, is the point. And a lot of the times, things were considered dissonant more because of beat frequencies or and stuff like that, rather than thinking about intervals. You know, in medieval music, everybody sang in perfect fifths because it sounded great. You know, the beat frequency was on point, whereas the fourth kind of has an ugly beat frequency, and I think that's why people were a little scared of perfect fourths and singing in fourths. So that's kind of the overview of how you calculate the Gradus function. But again, we have that issue with the human ear not really rounding correctly. So that's generally all I really have as far as Euler's Gradus function goes. Does anybody have any questions? Yeah, Caterpus, what you say is true. Generally, your brain wants to round to the nearest good fraction, if that makes sense. So if you're, in equal temperament, the perfect fifth is a little bit flat, and your brain just kind of rounds it to 3/2. This isn't always how to calculate the output again. Yes, so after you take the least common multiple, least common multiple of all your dudes. So N1, N2, N3, etc. Then you take out your resulting number. So let's just say this is big N, okay? So you're going to break n into its prime components. So p1 to the a1 times p2 to the a2 times p3 to the a3. So those are all the primes and then whatever exponents they happen to have, if that makes sense. Then what you're going to do is do 1 plus p1 minus 1 a1 plus a2 p2 minus 1 plus, and you're just going to kind of continue that pattern until you've done them all. So there are a lot of steps in doing it, and I'm sure you can find charts if you look up Euler Gradus function out there for like common intervals and what the function gives them. You can kind of decide for yourself whether the function accurately describes reality. I personally think it actually does a really good job as far as common intervals go. There's not many better alternatives. Some common alternatives to Euler's theory have came up more recently, like the last 40 years or so, and these usually have to do with beat frequencies and overtones. So, for example, what's the dude's name? I think like Helmholtz or something. What he looked at is, okay, let's say we have our one note A and our second note E. A equals 440 equals 660. Let's look at their overtone series. So we look through all of their overtones. You know, we can list out all the overtones there. And basically, the more that match up, the more consonant the interval is. Consonance has nothing to do with this. That also was a thing of Euler, but that has to do with Riemannian set theory. Yeah, no, Euler did invent the Consonance idea, but that has to do with like neo-Riemannian set theory and not serialism, but transformation theory and stuff like that. So I'll go over that another time. That's a really ugly formula, Dark Rifts. I'll take a look at that some other time. So yeah, this is Helmholtz theory, that the more overtones that are the same, that are shared between the two notes, the more consonant it is. Another theory has to do with the beat frequency. So for those unfamiliar, if you subtract the hertz of two notes, you get a beat frequency. So 660 minus 440 gives us a beat of 220. It's kind of like an optical illusion a little bit for your ears, acoustic illusion, whatever you want to call it. And his theory is the more that the beat frequency aligns with our two notes, the better that our interval will sound. So those are some more modern ideas. There's not as much going for them besides just the concept. A couple people have worked on it. The person that invented 22-tet worked on this sort of stuff a lot. Applications to composition, not really sure. I mean, this is basically just trying to mathematically describe what you already learned in composition class about consonant intervals. Well, think about it like this. I mean, if you play something that's 4 octaves apart, it's going to sound a lot worse than, 1 octave. There's less resonance. It's not necessarily that it's dissonant, per se. It's just less full, less rich. I mean, consonance is kind of a hard word to describe. The best way to describe consonance is absence of dissonance, Another thing that this theory doesn't describe that I really wish somebody would talk about is how intervals lower down sound a lot worse than intervals higher up. Like, for example, if I play a major third at the bottom of my piano compared to a major third at the top of the piano, the one at the bottom is going to sound like absolute garbage. And the interval up top is not going to sound as garbage, and Euler's theory doesn't really account for that. Yeah. No, that's the general idea, Caterpus, but what I'm saying is that Euler's theory doesn't really account for that. And there's not really many theories out there that are mathematically rigorous. Okay, I'm going to end the recording because this is probably taking up a lot of my storage space, but I'll continue to stream and answer questions.